Hello everyone, good evening students. Hope you all are doing good. Okay, we all started our classes for class 12. In the last class we started electric charges and field and we discussed till Coulomb's law. Hope you all remember that. Okay, today we will start from where we left behind, that is Coulomb's law. Let's recall what is Coulomb's law. This law comes when there are point charges Q1, Q2. Suppose they are separated by a distance R, then the amount of force acting between them is given by Coulomb's law. Do you all remember that? That is, force is proportional to product of the magnitude of point charges by square of the distance between them. That is, if we write it in SI unit, it was 1 by 4 pi epsilon naught Q1 Q2 by R square, and suppose we take these two charges in vacuum, then this is permittivity in vacuum, that is epsilon naught. Okay, do you all remember this? Okay, so here we have expressed this force, its magnitude only. Okay, and we know that force is a vector quantity. Okay, now we have to write it in terms of vector, that means in terms of its unit vector. Okay, so let's try to write it in the vector form. Okay, so here point charges are at rest. Why are these charges called point charges? Here they are separated by a distance such that the distance is much larger than its dimension. Its dimension is so small in comparison to the distance between them, so that they can be neglected. Okay, now let's try to write it in the vector form. So to write it in the vector form, what we need? We need unit vectors. Okay, so we have to define here unit vectors. Here, for that, we have to consider the charge, kind of positive charge or negative charge that we have in this charges. Suppose these two are positive charges. Clear? These two are positive charges. So here, if we want to find out what is the force on Q2 due to Q1, if these two are positive, this Q2 will be repelled away, there will be repulsion. So this is the direction of the force. Okay, that is force on 2 due to 1. Clear? Okay, so this is the direction of the force. Okay, as shown in the diagram. Okay, now define the unit vector, that is the vector which has unit magnitude and which gives the direction. So here, direction from 1 to 2. R1 to cap is the unit vector which gives the direction from 1 to 2. Okay, that means F21 is in the direction of R1 to cap. Okay, so this force on Q2 due to Q1. Okay, and we have represented by Q21 vector. It is what? By the Coulomb's law, 1 by 4 pi epsilon naught Q1 Q2 by R square. Okay, and what is its direction? Here it is directed from 1 to 2. Right, that is R1 to cap. Okay, clear? Okay, similarly, now what is the force on Q1 due to Q2? There will be force of repulsion as these two are positive. So here, this is the direction of the force acting on 1 due to 2. Acting on 1 due to 2. Am I clear? Okay. Now we will define the unit vector in this direction, that is direction from 2 to 1. That is R2, 1 is the unit vector which gives the direction from 2 to 1. Clear? Okay, so force on Q1 due to Q2, force of repulsion on Q1 due to Q2, it is what? Magnitude will be same in both the cases, Q1 Q2 by R square. And what is the direction here? it will be repelled in this direction, that is force is from 2 to 1, R21 cap. Okay, now see, these two are unit vectors, but they are opposite to each other. First one is from 1 to 2, second one is from 2 to 1. Equal and opposite, unit magnitude, same magnitude, but their directions are opposite. Okay, so we can write this R21 as minus of R12 cap, right? As these two are opposite to each other. Since they are equal and opposite, we can write this expression as 1 by 4 pi epsilon naught Q1 Q2 by R square, and this R21 cap is nothing but minus of R12 cap. Am I clear? Right. So now minus comes here. What remains? 1 by 4 pi epsilon naught Q1 Q2 by R square R12 cap. This is what? This is nothing but the previous force, that is F21 vector. So what we see here is the forces that are acting on these 2 point charges, their directions are opposite and they are equal in magnitude. Okay, so we even see that as these two are equal and opposite action reaction kind. So these two obeys Newton's laws of motion. Okay, am I clear? Okay, so this is the vector form of Coulomb's law. Okay, till now we have considered 2 charges. Okay, now suppose in the body we have supplied many charges, right? Okay, for simplicity we'll just start with 3 charges. Suppose there are 3 charges. This is Q1, Q2 and Q3. Okay, and for simplicity we write the distance between them, that is Q1 to Q2. This much distance is R12, and the distance between Q1 Q2, that is this much distance, is R13. Okay, now we want to find out what is the total force on Q1, that is what is F1. Okay, so we can find out this total force by the principle of superposition of electrostatic forces. Okay, now here see what it gives when a number of charges are interacting. Okay, then the total force on the given charge is what? Vector sum of the forces exerted on it. That means now first we'll find out the force on Q1 due to Q2, then force on Q1 due to Q3, then we will check their vector sum. Okay, and when we find out the force on Q1 due to Q1, we will consider as if Q3 is absent. Clear? That means it is not affected by the force between 2 charges, is not affected by the presence of other charge. Clear? Okay, so let's find out the force on Q1 due to Q2 first by neglecting Q3. Clear? Okay, so here force on Q1 due to Q2, right? It is what? 1 by 4 pi epsilon naught Q1 Q2 by R12 is the distance between them square, and direction is R12 cap, right? Okay, and here see what is the direction here. These two are positive, suppose, so Q1 will be repelled away by Q2, right? So this is the direction of the force acting on 1 due to 2. Clear? Am I clear? Okay, now so when we are finding out the first force, we are neglecting, so Q treat as if it is not affecting the presence here. Clear? Okay, now what we will do is, now we will neglect Q2 as if it is absent, because it will not affect the force on Q1 due to Q3. Clear? So now we will find out force on 1 due to 3. So here these two are positive again. Okay, so here Q2 will be repelled away from Q3. That means it will move in this direction. It will experience force away in this direction. Okay, so here this is the direction of what? Force F1 3, force on 1 due to 3, right? Okay, so what is the magnitude of that? 1 by 4 pi epsilon naught q1 q2 by, what is the distance between them? r13, right? r13 square, and we write the unit vector as r13 cap. Okay, so now here these two are the individual forces acting on this. Now by the principle of superposition, total force will be the vector sum of the forces exerted on it. Clear? So here F1 will be F1 only, total force on the charge Q1. It is what? F12 plus F13, the sum of these two forces acting on the body. Clear? Okay, this is the principle of superposition. Now suppose there are n number of charges q1, q2, q3 and so on up to qn, then total force on q1, that is first point charge, will be F12 force on 1 due to the second, then F13 force on 1 due to this third, then F14 and so on up to force on 1 due to the nth point charge. Clear? Am I clear? So this is the principle of superposition of electrostatic forces. Clear? Okay, now till now we have discussed that there is some force of attraction or repulsion between the charges. Okay, now what amount of forces are acting at different point? We will discuss that here. If we have the point charge q, suppose here, okay, then if we keep this point charge q not far away, okay, such that it does not experience any force due to q. Okay, suppose these two are positive and this charge q naught is so much far away that it does not experience any force on it. So we say that it is not in the electric field of this charge q. Okay, that means it does not experience any force of electrical origin at this point. Okay, so here we define electric field at a point as it is said to exist at a point if the force of electrical origin is exerted on the stationary charged body. We have taken stationary charged body as q naught placed at that point. That means there is no electric field. It is not experiencing any force of electrostatic origin. Clear? Okay, now we will slowly bring it near to it. Okay, by doing some work. Okay, we are moving it from outside. Now if I bring it near to it, suppose here, okay, at first here q naught. Okay, now it will start experiencing repulsion. That means it will due to this q. That means at this point, suppose this point is P, for example, at this point it is experiencing the electrostatic force of which origin? Stationary charged body. This is the force due to this charged body q, which is stationary, kept fixed there. Okay, so it is experiencing the force of electrical origin which is exerted on the stationary charged body placed at that point. Okay, that means there is electric field at that point. Am I clear? Okay, so this is the concept of electric field. Now here see, now I will move it closer and closer. Suppose here, suppose q naught is here. Now here, if we compare this two, in these two cases, in which case the force experienced will be more? Obviously in this case q, right? That means here the value of electric field will be more. That means if we want to find out the strength of the electric field at this point, these 2 points, as the amount of field acting is different, force acting is different. We want to find out the strength of the electric field at the different points, which will be different. Okay, and we defined it as electric field intensity at the point. Am I clear? Okay, and how do we define it? Here we have taken this point charge q naught here, suppose, and because of this charge q, it is experiencing the force of electrostatic origin F. That means q naught will experience force F. Now, if we take unit charge, one charge, what is the force experienced by it? That is F by q naught. Okay, this force experienced by unit charge placed at this point gives the electric field intensity. Am I clear? Okay, so here what will be the definition of electric field intensity at a point? It is what? Force experienced by unit positive charge test charge. Okay, because we are placing this charge to measure the electric field intensity. Okay, so for that, experienced by unit positive test charge placed at that point. Clear? Okay, so this is electric field intensity. Okay, and we represent this electric field intensity by E, that is F by Q. Okay, and now this electric field intensity is a vector quantity, and what will be its direction? It is F by Q. That means its direction is same as the direction of the force experienced by it. That means this is the direction of the electric field intensity even. Clear? Okay, and now let's see its unit. Who's the SI unit? Okay, so here what is its unit? It is F by Q, right? So what is the SI unit of Newton? Force, that is, sorry, the answer I told already. SI unit of force is Newton by, what is the SI unit of charge? That is Coulomb. Okay, so the SI unit of this electric field intensity is Newton per Coulomb. And now what is the dimension? I think you all know already what is the dimensional formula of Newton. That is force. Force is what? Mass into acceleration. Dimensional formula of acceleration is L by T square. Okay, I hope you all remember this. I don't have to do this one. Okay, ml t to the power minus 2. This is the dimension of force by, now we have charge. Okay, what is the dimensional formula of charge? Think you all remember this from your class 10's knowledge. Charge is current into time. Okay, and the dimensional formula of this current is ampere, and this time can be represented as capital T. Okay, so here the dimensional formula will be A into T. Okay, so here what you'll have? ml t to the power minus 3 a to the power minus 1. Okay, am I clear? Now we have defined electric field intensity at a point. Now we'll find out what is electric field intensity at a point due to a point charge. Okay, so here this is the point charge Q. Now we want to find out what is the electric field intensity at this point P. Okay, electric field intensity due to this point charge Q. Okay, now to find out intensity, what we have to do is we have to consider a test charge. We'll place a test charge, positive test charge Q naught at this point P. Okay, then we'll find out what is the force acting on this Q naught. Okay, so for that we'll consider the distance between them. Suppose the distance between them is R. Okay, so here we are imagining a test charge Q naught at point P, which is at a distance R from the point charge Q. Okay, then according to Coulomb's law, what is the force acting on Q naught? The force of repulsion, as these two are positive, Q naught will be repelled away. Okay, and what amount of force will be acting on it by Coulomb's law? 1 by 4 pi epsilon naught product of the charges. What are the charges here? Q into Q naught by what is the distance between them? R. So here square of the distance between them. We are just interested in the magnitude here. Okay, so here this is the force acting on it. And what is the electric field intensity at this point? Its definition is its value is given by F by Q naught, right? That means it is the force acting on unit positive charge placed at that point. That is, now if we put the value of this F here, what will get cancelled? This Q naught gets cancelled. So what we'll have here? 1 by 4 pi epsilon naught. Let's do it once. Q naught by R square, and now we divide it by Q naught. So this 2 gets cancelled. 1 by 4 pi epsilon naught Q by R square. Okay, so this is the amount of field intensity at the point P at a distance R from the point charge. So it depends on what? On the source, that is Q, and not on the magnitude of test charge. Okay, so this is the significance of electric field intensity. It is the property of the source, that means here of the charge, which is the source of the electric field, which is the source of electric force acting at this point P. Okay, clear? Now let's move. Now here see, in the previous case we had considered only one point charge, right? Q. Now we'll consider many point charge. Suppose Q1, Q2, Q3 and so on. As before, now if we want to find out, suppose this is the point P, we want to find out the test charge, the electric field intensity at this point P. So electric field intensity at this point P will be what? 1 by 4 pi epsilon naught. Due to first one, it is what? 1 by 4 pi epsilon naught Q by square of the distance between them. Okay, suppose the distance between them is R1. Square of the distance between them, right? And due to the second one, 1 by 4 pi epsilon naught Q2 by, suppose here the distance is R2, this distance is R2, that is R2 square. And here let's write the unit vector even, because this is the vector sum. Okay, from the principle of superposition, total field intensity will be vector sum of all the field intensities. Okay, so we even have to consider the unit vectors, because we have to consider the direction even. That is here in the third case, the field intensity at this point due to this point charge Q3 will be Q3 by square of distance between them. That is distance of this point P from Q3, that will be suppose R3. So that this is R3 square. Unit vector is R3 cap. Okay. So here if we write this as R1 naught for simplicity, 2 naught, 3 naught. Okay. This point as origin here. So this is the total field intensity at the point P due to all these point charges Q1, Q2, Q3. It is what? Vector sum of all the field intensities acting at that point P due to all the point charges. Clear? Okay. Now if we consider there is one charge here, okay, any kind of charge. Now if we bring some unit charge, positive unit charge, suppose 1 Coulomb. Okay, now here see, if this is positive charge, this will get repelled away. Okay, then suppose this is moving in this direction in this case, and here also after some time it reaches here, then at this point even it will experience force of repulsion and again it will move away. That means it will move along some path due to this force, electrostatic force of repulsion. Okay, this curve along which this unit positive charge is trying to move, it is tending to move. Even if it is at rest, kept here, it will try to move in this direction. Okay, so it will tend to move in along some direction along a curve. That imaginary curve is called electric lines of force, and the arrow sign here gives the direction of the motion, direction in which it is trying to move. Okay, so here its definition, first line says what? Electric lines of force are defined as the curve along which a small positive charge would tend to move when free to do so in the electric field. That means here we have placed this unit positive charge in the electric field of this charge. Okay, then because of the electrostatic force, it is trying to move along this curve. Okay, this imaginary line along which it is tending to move. Okay, this imaginary curve is called its electric line of force. Okay, now suppose, now forget about all this. Okay, so for that let's erase this one. Suppose this is the electric line of force. Okay, now here we have discussed an electric field. At a different point there are different strengths of electric field. Different amount of forces are acting. Okay, and we have defined it as electric field intensity, and it is a vector quantity, right? Electric field intensity was a vector quantity. It has some direction, right? Okay, now we want to find out, if this is given as the electric line of force, we want to find out what is the direction of the electric field intensity at that point. So here suppose we are at this point P and we want to find out the direction of the electric field intensity at this point. So for that we will draw a tangent at this point. Okay, so the tangent at this point will give the direction of the electric field intensity at that point. Okay, this completes the definition of electric lines of force. Okay, so here let's see the definition. The curve along which a small positive charge would tend to move when free to do so in an electric field. And what we are doing, we are drawing a tangent at this point, gives the direction of the electric field at that point. Clear? Okay, now let's try to draw the electric field lines due to this positive charge. Okay, so here if we take any small positive charge, it will get repelled away from it. So this is the direction of electric field, in this direction. Now if I keep the positive charge here, again it will get repelled away. It will tend to move in this direction. So this is the direction of electric lines of force. Now again if I place the point charge here, small positive charge here, it will move away because of the electric field, because of repulsion. So this is the direction of the electric lines of force, in this direction here. Again if I place a positive charge, it will move, it will tend to move in this direction, which will give the electric field lines. Am I clear? Okay, now see, let's see the example of all this here in the diagram. For the positive charge, these are the electric field lines which are directed away from the positive charge. And here see, now if I place some positive charge here, it will get attracted by this negative charge, so it will tend to move in this direction. That means the arrow sign shows towards the negative charge. Okay, so here lines of electric field lines will be towards the negative charge. Okay, now see here what will happen if we have placed positive and negative together, right? Okay, so here the positive charge will move away from it and towards the negative. So these are the electric field lines which will be produced due to these two positive and negative charges. Okay, so here from here what we see, what is the property of the electric field lines? They start from positive charge, they end in negative charge, right? Okay, so starting from here they are ending it here like this. That means it is smooth continuous curve which without any cracks in the middle, right? It is a smooth continuous curve, okay, but it does not form a closed loop. It cannot form, it doesn't form closed loop. Okay, so here in this case positive and negative, starts from positive, ends in negative. But what happens if we only have the positive charge? In this case it will start from positive charge and it will end in infinity. Clear? Okay, so let's discuss the properties of the electric field lines. First property is electric field lines are continuous smooth curve without any breaks, we have discussed. Second one, the lines of force start from positive and end at negative charge, we saw that. Positive and negative start from positive, end in negative, or end at infinity for a single positive charge. For a single positive charge it will start from it and it will end in infinity. They cannot form closed loops. Okay, and now third property, this we discussed in the definition only. If this is the curve here at this point, what is the electric field intensity? Direction of electric field intensity, its direction will be given by the tangent drawn at this point. The tangent to a line of force at any point gives the direction of the electric field at that point. Okay, and now we have to discuss the other properties, right? Okay, now for that, if we consider here, suppose now let's see this one only. No two lines of force can intersect each other. This is the property. Now let's see what will happen if they intersect each other. Yeah, okay, suppose these two field lines are intersecting at this point. Okay, so here it is, field lines direction is in this way, in this direction. So here at this point, what is the direction of field intensity? If we consider this curve only, this first curve, this is the direction of field intensity at this point. Okay, now if we forget about this, now if we consider the second curve, what is the field intensity at this point? Direction, it will be in this direction. That means these two curves are showing two direction of the field intensity at the same point, which is not possible, because at a given point field intensity has some fixed direction. Total field intensity has a given fixed direction. Okay, so here no two lines of force can intersect each other. If they intersect, then what will happen? There will be two tangents at the point of intersection, which will give what? Two direction of field intensity at the same point, which is not possible, because at a point the electric field can have only one direction. Okay, now another property is, if this is the conductor, right, then lines of force will be normal to the conductor. Lines of force are always normal to the surface of conductor on which the charges are in equilibrium. Charges are in equilibrium means what? Inside the conductor, charges can flow freely, okay, until equilibrium has reached. Okay, when there is equilibrium, in that case, the conductor, the lines of force for the conductor, it will be perpendicular to it. It is normal. Okay, that means here it cannot be at some angle, right? Suppose this is the direction of electric field lines. Okay, now what we will do is, I'll consider the case, suppose the field lines are at some angle, okay, and it is not at 90 degree. If it is not at 90 degree, if it is at some angle, what will happen? Then let's see, suppose the direction of electric field lines is in this direction, and at this point the tangent will give the direction of field intensity. That means it will give the direction of force at that point. Clear? So this is the direction of force if field lines is at some angle but not at 90 degree. Clear? Then from vectors, from the rectangular components, we can break this vector into two components. One is f cos theta in this direction, another is f sin theta. Right? Okay. Then here, if there are charges here inside the conductor, they will experience some force, parallel force f cos theta in this case. That means if it is experiencing force, it will move because inside the conductor charges can move. But what we see is in equilibrium, charges are at rest. They will not move. If these charges are moving, they will form what? Current. And inside the conductor there is no current formed when it is an equilibrium, when it is not connected to any wire. Clear? Okay, so this force doesn't exist. That means this part is zero. So from here what we can conclude is this force cannot act at some angle, any angle, but it acts at 90 degree. It doesn't have any parallel component. If it has parallel component, there will be some surface current produced in the conductor without any source. Okay, understood? So lines of force are always normal to the surface of conductor on which the charges are in equilibrium. Clear? Okay. Now next property is the lines of force have a tendency to contract lengthwise. Okay, this explains attraction between two unlike charges. For that, let's consider one case. Suppose the electric lines of force from positive to negative. This is one electric field line. Okay, drawn from the positive charge and the negative. Between the positive and negative charge there is what? Attraction. And what the property is saying here is this line of force, they have tendency to contract lengthwise. That means they will tend to have minimum length. They have a tendency to contract lengthwise. This is similar to surface tension. I think you all remember it. You all did it in class 11. The surface of water, here they will experience some tension, surface tension, because of which it will tend to have minimum surface area. They will tend to contract. They will tend to come towards each other because of attraction. Right? Okay. So here also there is attraction between unlike charges. So here the field line of force, they will tend to contract lengthwise. Okay. They will try to have minimum length. Understood? Okay. As we have seen, lines of force start from positive charge and end in negative charge. Okay, so this is one of the property of electric field lines. Okay, now second property is relative closeness of the lines of force give a measure of the strength of the electric field and in any region. Okay, so for that let's consider a figure. Here see in this region the field lines are far away from each other, right? And as we move away, you see, field lines are closer to each other. Okay, when the field lines are closer to each other in this region, here, electric field will be more, strength of electric field will be more. And as we move here in this direction, as the electric field lines are moving away from each other, then the electric field strength intensity will decrease here. Okay, so the relative closeness between the lines of force gives the strength of the electric field intensity. Clear? Okay, so this is called non-uniform electric field. Okay, so here at this point, strength of electric field is more, and at this point strength of electric field is lesser. Okay, so is it uniform? Electric field, is it uniform? In this case it is not, right? So this is called uniform, non-uniform electric field. Okay, now if the electric field is uniform, strength of electric field is same, so in that case we will draw lines parallel to each other and they are equispaced. Okay, so if we have field lines parallel to each other and they are equispaced, the space between them are equal everywhere, then this field is called uniform electric field. Clear? Okay, now let's go back to the property of the electric field lines. Last one that we need to discuss. The lines of force do not pass through the conductor because the electric field inside the charged conductor is 0. Okay, so here see, if we take a conductor here, then electric field inside, net electric field will be 0. Okay, if we place it in the electric field, what will happen is this will induce negative charge here and positive charge here. We will discuss this in detail afterwards and it will be more clear. Okay, so that now inside even the charges are separated, so what they will do is they will nullify the effect of the electric field which is passing through it. That means net electric field inside it will be 0. Net electric field inside it will be 0. Okay, because there is redistribution of the charges inside the conductor when it is placed in the electric field. Okay, so when we place it in the electric field, charges will move in different directions until field inside the conductor becomes 0. Okay, so electric field lines cannot exist inside the conductor diagram. What we have done is we have taken positive charge to positive charges, that means there will be repulsion, so here field lines will be as given in this figure. Okay, moving away. Okay, understood. Now one last thing, we'll do this one. Okay, we'll discuss this one. This figure shows electric lines of force due to the point charges Q1 and Q2. As I had shown before, do you all remember? There is repulsion. Field lines are moving away. So what is the nature of charge on them? This two should be like either positive positive or negative negative if we see this one. But now see here, even the direction of field lines are given, right? Field lines are moving towards it. That means here, what is the property? Field lines start from positive, end in negative. That means it is ending here. That means this should be negative. Here also it is ending here. So this charge should be negative. So what is the answer here? The nature of the charges on them is negative. Okay, then last question for this electric lines of force. A positive point charge plus Q is kept in the vicinity of uncharged conducting plate. We have uncharged conducting plate which can develop charges if placed in the field, right? Now we have one uncharged. Okay, let's place it near only so that it's easier to draw. Okay, we have kept positive point charge Q here. Okay, then what kind of electric field lines will exist? Okay, now see, because of the presence of this charge, this will experience some electrostatic force. Okay, that means here the charges will get disturbed and this face will develop negative charge as this one is positive. Induced negative charges will be induced by electrostatic induction and here positive charges will be induced, right? Okay, so the field lines will start from this and end in the conductor. Okay, and how this charges, this conductor. In this case, here the field lines will start from it and end on it at 90 degree. They will be normal to the conductor. This is the one of the property of the field lines. What is the property? They will meet the conductor at 90 degree only normally, not at any other angle. Okay, so this is the answer. Electric field lines will originate from it and end on it at 90 degree, and on it at 90 degree. Clear? Okay, so these are the electric field lines originating from Q and ending on this conductor. Clear? Okay, now the last part of today's class that we need to discuss. Do you all remember this permittivity which came when we discussed Coulomb's law? Okay, I said we'll discuss about it in detail afterwards. I wanted to discuss about this when we have discussed electric field lines only. Then it will be more clear to understand it. Okay, let's recall permittivity. From where it comes? It comes from Coulomb's law, right? Okay, so for that we'll consider 2-point charges Q1 and Q2. Suppose first one is positive. For simplicity to understand nicely, we'll consider this second one as negative. Okay, then what is the force? And we'll place this in vacuum. Okay, medium is vacuum. Then what is the force between them by Coulomb's law? 1 by 4 pi epsilon naught. This is the permittivity in free space. Q1 Q2 by R square, right? Okay, this was the force in vacuum. Okay, now we'll consider the second case. If we take this, immerse this inside the glass. Okay, suppose, or in water. Okay, we immerse this one inside water. Medium is water. Then the force in the medium will be what? Suppose the permittivity in water is epsilon. In that case, 1 by 4 pi epsilon Q1 Q2 by R square. Okay, so in these two cases, what is different? This constant value, that is epsilon naught, and epsilon is different. That means the magnitude of these two forces acting between two same charges which are separated by the same distance, but the medium is different. The forces will be different. That means if different mediums are used, the force acting between them will be different, and the property which gives that the different amount of force will be acting on these two charges is called permittivity. Okay, so here comes the definition. Permittivity is called, it is the property of the medium which determines the electric force between two charges situated in the medium. Okay, so this is just the definition. Now let's try to understand it more clearly. Okay, what will happen? Why is the force decreasing when we are taking these two charges inside water? Okay, so here inside water, this is the first charge plus Q, this is the second charge. Okay, let's draw the bigger diagram. This is plus charge, this is minus charge, and it is placed in water, inside water. Okay, and what we know is electric field lines will be acting between them, which gives the force between them. What amount of force is acting between these two charges? Okay, now because of the presence of the medium, what will happen is this field lines will change. Okay, just think about this as the threads, for example. Okay, how it will change, we will discuss it afterwards. Okay, for now just understand that this field lines will change. Okay, that means all the threads which are starting from Q1 to Q2, they will not reach Q2 Q2. Okay, that means some of the threads are absorbed by this medium. That means the net force experienced by this Q will be lesser. Okay, clear. That means field is reduced because of the presence of the medium. What is reduced? The field is reduced. Okay, that means some of the electric field lines will be absorbed. That means now the number of field lines will be decreased. That means less number of field lines means strength of electric field will be less. Strength of electric field is less means force acting between them will be lesser. Understood? Okay, so when there is presence of the medium, the field is decreased. Okay, how it decreases, we will see it afterwards in the next chapter. Okay, the field decreases, that means force acting between them will be changed. That means here, and by what amount it will change? It is given by this amount epsilon, which is called permittivity. Okay, now we want to compare by what amount this force is decreasing. Okay, so when we have to compare, what we will do is we will divide this to, okay, I'm writing it here. So we will divide this force of vacuum by force in medium. Okay, so here what we'll have? 1 by 4 pi epsilon naught Q1 Q2 by R square by 1 by 4 pi epsilon here in this case Q1 Q2 by R square. This all gets cancelled. What remains? What we have here? This epsilon comes in the numerator. Epsilon by epsilon naught. Okay, and we define this ratio as relative permittivity. Okay, relative permittivity, and we write it as epsilon R, and sometimes we write it as K, which is dielectric constant. Dielectric is the other name of insulators, okay, which are not good conductors of electricity, through which charges cannot flow easily. Clear? Okay, so here we want to compare the force, by what amount the force is decreasing in the medium, okay, in comparison to the force in vacuum. When we are comparing these two, we get a quantity, we get a ratio epsilon by epsilon naught, and we define it as epsilon R, which is called, and we define it as relative permittivity or dielectric constant. Okay, the ratio of permittivity of the medium to the permittivity of free space is called relative permittivity or dielectric constant of the medium. Okay, and here from where we started, this K is what? ER is what? It is F of vacuum by F of medium. Okay, so now first definition we saw as ratio of epsilon by epsilon naught. This is the second definition of relative permittivity. It is what? Ratio of the forces. One, in the first case, the same charges separated by same distance, it is taken in vacuum, and in the second case it is taken in some another medium, for example water. Okay, so this is the second definition. It is the ratio of the force between two charges placed some distance apart in free space. That means here free space means vacuum, to the force between the same two charges when they are placed in the same distance apart in the given medium. Okay, so this is the second definition. Okay, so why this relative permittivity comes? We want to compare by what amount the force is decreasing. Okay, so from here, if we take this on left hand side, what we'll have here? Force in the medium is equals to force in the vacuum, and we take this relative permittivity in the right hand side, we'll get okay. So now see, what is the force in the medium? It is 1 by K times the force acting in the vacuum. That means this will decrease K times the force acting in the vacuum. Okay, if for water K is 80, then force in water will be Force in vacuum by 80. So it will decrease by 180 times. Okay, 1 by 80 times the force between the same charges when it is placed in vacuum. Okay, so here we define this relative permittivity to write the force in terms of the force acting in vacuum. I hope it is clear. Okay, so depending on this, let's see two questions and then we will end our class. Okay, so here first question says what? Two equal balls having equal positive charge q coulombs are suspended by two insulating strings of equal length. Okay, that means here two positive charges, they are having equal charge, they are suspended by two strings of same length, and because of repulsion they will move away, right? This is our case, right? What would be the effect on the force when the plastic sheet is inserted between the two? Okay, initially it is vacuum. In the vacuum, force acting between them is F, suppose F vacuum, right? Now if we place this in, place some plastic sheet in between these two charges, then what we know is when the medium is changed, force will decrease by what amount? 1 by k times the initial force. So what will happen to the force? Force will decrease by how much amount? 1 by k times the force acting initially. Okay, so this is our answer. And the last question of our day is the force between 2-point charges kept at a distance d apart in air is d. 2-point charges are, that is q1, q2. कसरी separate करेक्सा distance d. Okay. Then the force acting between these two is F. Okay. Now if these two charges are kept at the same distance in water, now we are placing these two same charges in water. How does the electric force between them change? Now the force in water will be 1 by k times the initial force, and for water what is the dielectric constant? It is 80. So 1 by 80 times it will decrease 1 by 80 times the initial value of the force. Okay, clear? Okay, now please like and subscribe and share it to your friends even. Till then, study well and stay safe.